We're going to start working on Chapter 6, Day 4, some homework. All right? So this is going to be question Chapter 6, question 66. All right? That's what it's called. And the question is, which of the orbitals are spherical? All right? So the different kinds of orbitals. What are the different kinds of orbitals? There's S, P, D, F, G, and theoretically you can go higher, H, I, J, and so forth in terms of excited conditions, right? Because electrons in ground state, that means when the electrons are around the atom as low as they can be, as close as they can be. You can't all be in the first 1s orbital, for example, because each orbital only holds 2 electrons, right? So you have multiple different orbitals and shapes, and these again correspond to the L values. L equals, for these ones, 0, 1, 2, 3, 4, and so forth. On our periodic table, we have, here's a little periodic table for us. We have the L values corresponding to L equals 0 here, L equals 1, the P block, L equals 2, the D block, and L equals 3, the F block. All right? So that's what our L values correspond to. So the spherical one is L equals, or the S orbital when L equals 0. That's spherical. And a way to remember that is S is spherical. P, the P are dumbbell shaped. One orbital looks like that. The D are also dumbbell shaped, but each orbital has 4 lobes on it. They're in different directions. And actually the 5th D orbital, I don't know if you remember, but it looks like this with a little donut around it. All right. So this is what P orbitals look like. D orbitals look like this in different directions, or the 5th one looks like that. Okay, and F orbitals, again, they're multiple lobes around the center. But SPs and Ds are as far as you really kind of would like to be aware of. Again, nothing that's going to be terribly important to know. All right, so the next question is radial probability distributions. All right, so we get these graphs, and these graphs are showing us probability of the probability of the electron being at any certain point. This is our 1s, our 2s, and our 3s. And in the 1s, you see the probability and the distance from the electron, right? So the probability in a 1s is that your electron density is going to be this far away from the nucleus, the center. In a 2s, there's a slight probability it's there, but there's more probability that it's in this region, right? In the 3s, there's 3 regions of probability, and again, you have your nodes in between. So essentially what this is doing is it's like taking the S orbital, and so here is the spherical shape of the orbital, right? And the nucleus is here in the middle, and we're looking at where the electron density would be. If I'm going to kind of draw where the electron density would be with by adding dots, kind of like a probability map, then the dots would be around the middle mostly. There would be some few around the outside, but mostly the darker area would be in the middle, right? So this would be kind of like a probability distribution of where the S orbital would be. And these pink areas are the distribution of how far away the electron density is going to be. Now this is, go figure 618. All right, and so the first question is, how many maxima would you expect to find if in the 4s orbital of the hydrogen atom? Well, in the 4s orbital, you would expect to find, as you see in the 1s orbital, there's 1 maxima. In the 2s, there's 2. So in the 4s and 3s, there's 3. So in the 4s, you would expect to find that there are 4 regions of at least the maximum, right? How many nodes would you expect to find? The nodes are the regions where there is no electron density. So here in the 1s, there's no real nodes. In the 2s, however, you get this. I mean, theoretically, this could be a node and that could be a node. But the node is where it's in between 2 regions of density. So this actually goes down to the bottom like that. So there's theoretically no electron density in that node there. So as you get 2s, you get 1 node. 3s, you can see there, you get 2 nodes. So the nodes is going to be 1 less than what it is. We're talking about 4s, so that's going to be 3 nodes, right? All right, so the next question. The condensed electron configuration for aluminum, all right? This is chapter 6, question 18. The condensed electron configuration of aluminum, element 13. So what's the condensed electron configuration? Well, we have to look at our periodic table and look at aluminum, and then we go backwards. Here's aluminum. We go backwards to the nearest noble gas. So the nearest noble gas is neon. Neon has 10 electrons, and so aluminum has what we call a neon core, and then 3 extra electrons on the outside, right? So the neon core is identified in our abbreviated electron configuration just simply by doing that. And then we add on the rest. So after neon, we look at our periodic table there, and we see the next electron, the one which is sodium and magnesium and then aluminum. The sodium is in the 1, 2, 3, it's in the 3rd row down, and that is in the S block. So that's 3s1 and 3s2 for sodium and magnesium. So we have to put in here 3s2, and then the 3p for aluminum would have 1 electron. So that would be our electron configuration for aluminum. All right, and then the condensed electron configuration for arsenic. So this is question 19 there. And they might be asking you a different element, but this is element 33 for this question here for me. And I can see that if I go backwards from arsenic, number 33, the first noble gas that I run into is argon. So argon is going to be my noble gas core, which I use, right? And I need to add on after argon. It's 18 electrons. I need to add on some more. Right, so for arsenic, right, element 33, argon's our noble gas core. And then after argon, we have to put 2 4s's in. 4s2, that's for potassium and calcium. And then we have 10. Now this is the tricky part. This is the D block, right? The D block. And we have 10 electrons going in. But this, remember, it's in the 4th row, but when you go to the D's, you start 1 number lower. So 3D10 fills up first. That's scandium to zinc. And then we need 3 electrons. It's in the 1, 2, 3, 4th row. So that's 4p3. And that should be our electron configuration for arsenic. Okay? So, the next one, there are how many unpaired electrons in the ground state of oxygen? So this is chapter 6, question 12. All right, so in oxygen, what's the electron configuration for oxygen? We have to draw the electron configuration for oxygen. It would be helium, 2s2, and then 2p, 1, 2, 3, 4. All right, now from this, we can draw what's called an orbital diagram. We kind of identify what these electrons look like in terms of their energies and how they're filling up orbitals. Now, we don't need to know what helium looks like, or the core, because unpaired electrons are only going to be the ones that are outside the noble gas core. All right, those are called, the ones with the highest N value at least are called valence electrons. So in this case, we have the highest N value of this oxygen, so this is oxygen atom, is 2. So these 2 electrons and those 4 electrons, a total of 6, are all considered valence electrons. But we'll draw the whole orbital diagram for everything. So here's how you draw the orbital diagram. you start off with the electrons that are here. Now, helium has a 1s2 electron configuration. So we draw a little line. And this little line, again, we can label it 1s. It represents the 1s. And in the 1s, it holds 2 electrons. And we draw those 2 electrons as arrows. Now, the arrow can go up, and one arrow goes up, and one arrow goes down. The up and the down is indicative of the different m sub s quantum number, which is spin, plus 1/2, minus 1/2, right? So, we have 1s2, that's what the helium is here, 1s2. I'll write the non-condensed form, non-noble gas core form right here above it. 1s2, 2s2. So the next electrons have to be in the 2s, and there's 2 electrons as well there, 2s2. And the next electrons have to be in the 2p. Now the 2p, how many orbitals are there in the 2p? Well, I don't know if you remember, but there's the px, the py, and the pz. Right? So pz actually kind of be in front there a little bit. So there's 3 orbitals. Each orbital holds 2 electrons, a total of 6, and that's why there are 6 elements going across here in the p block of the periodic table, right? So, how many electrons does oxygen have there? Just 4. So, the rules for filling an orbital diagram. You have to start with 1 electron in each. So we need to get 4 electrons in here. And I put 3 in so far, and now I can put my 4th electron. I can't pair up an electron until every orbital has at least 1. So there's the 4th. Now there's 2 of them that end up being unpaired. All right. So there's a couple ways to visualize this. You could have visualized it with these orbitals and said, I need to put 4 electrons in there, and maybe start shading them. There's 1 electron here, 1 electron in this orbital, 1 electron in this orbital, and then the 4th one. Now each one has one. The 4th one has to go into an orbital that already has an electron. All right. So this is a paired orbital. These ones are unpaired. So how many unpaired electrons does oxygen have? It has 2 unpaired electrons. All right. So based on the structure, so this is Give It Some Thought 611. All right, so based on the structure of the periodic table, which becomes occupied first, the 6s or the 5d orbitals? So you can look on here on the periodic table and look at 6s. Where's 6s? Well, it's 1, 2, 3, 4, 5, 6, right? 6n is 6, so it's the 6 column down, and s block, these are them right here. So these get filled. I mean, the question is, what gets filled first, this or the 5d? Well, where's the 5d? Well, I know these are the 3d, 4d, and 5d. So the 6s and then the 5d. Well, if you're filling, starting from 55, 56, 57, the 5d, or the 6s get filled before the 5d begin. All right, so 6s, whoops, 6s has to be the answer there. 6s gets filled before the 5d does. And that's simply by looking at the periodic table. Okay. 6-20, or chapter 6, question 20. The largest principal quantum number in the ground state electron configuration of potassium. So we look at potassium on the periodic table, and we want to know the largest ground state, largest principal quantum number. The principal quantum number is n. So principal quantum number, quantum number is n. All right, so the principal quantum number is n, and what is the largest n value for potassium? Well, if I look at potassium, I see that it is in the 1, 2, 3, 4th row. It has some 4s electron. It has one 4s electron, right? So 4. N equals 4 is the highest principal quantum number. It has n equals 3, n equals 2, and n equals 1, but n equals 4 is the largest principal quantum number. All right, question 8. The ground state electron configuration for zinc. So this is chapter 6, question 79. And we're looking for zinc. We want to know the electron configuration for zinc. It has 30 electrons. The argon is the noble gas. Going backwards is the next noble gas as you go backwards from zinc. After argon, we need two 4s electrons. So 4s2, that is 1, 2, 3, 4. That's potassium and calcium. And then we need 10, whoops, there goes the superscript there, 10 3d electrons. All right, so here we have the ground state configuration of zinc. Now, a question that you're not asking yourself, but something that we should be aware of, is how many valence electrons does zinc have? Zinc has 2 valence electrons. Now you say, well, why didn't we choose these? Well, valence electrons are always the ones that have the highest n value, the highest principal quantum number, which in this case is 4. So those 2 are valence electrons. These ones we call pseudo-valence electrons because they kind of confuse us sometimes, and they are useful for certain things, and we'll sometimes get into talking about that. But for now, this is the ground state configuration for zinc, the abbreviated ground state configuration for zinc, and it has 2 valence electrons. All right. The elements in the blank period of the periodic table have a core electron configuration that is the same as the element electron configuration of neon. All right. So this is chapter 6, question 83. So, what elements in which period, right, have a core electron configuration that is the same as the electron or configuration of neon? So, the elements in the blank period of the periodic table have a core electron configuration the same as neon. So, if you look at neon, right, here's neon. It has 10 electrons. That's 1s. 2s2, 2p6, right? That's filling the first shell and the second shell completely. So that is neon. That's the electron configuration for neon. Just a second. Okay. So that's the electron configuration for neon. And what other elements have this as their core? All right. If you get up to argon, then everything beyond argon would be considered as having argon as its core. So that wouldn't be necessarily just neon as its core. But the electrons from sodium all the way to chlorine would be considered as having neon as its core, right? So that is the third period there. All right. So let's see here. Third period is an option. All right. The next one. Problem 670. Write the condensed electron configuration for germanium, gallium. Express your answer in condensed form in order of increasing orbital energy as a string without blank spaces between orbitals, for example, like that. Okay? So, in this one here, let's see, we have 1, A, B, C, D, E, F, G, H, I, J, K, L, M, N. Alright, so we look at gallium. We've talked a little bit about how to do this already, but we're looking at argon as the core electrons. Argon, you go back from gallium, find out where the first noble gas is when you're going back from gallium. That's your core. And then we have 4s2, 3d10, 4p. How many for gallium? 4p1. So there's our condensed electron configuration for gallium. Indicate how many unpaired electrons gallium has. So this 4s2, you can imagine the 4s orbital, and it's going to have 1, 2 electrons in it. The 3d10, now the d orbitals, there are 5 of them. So if this is my 3d, and I begin to fill them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're all filled up, so none of those are unpaired. The 4p, which is the next one here, 4p has only 1 electron in it. So what was the question? Indicate how many unpaired electrons there are. There's 1 unpaired electron. Write the condensed electron configuration for calcium. All right, calcium is going to be argon with just the 4s2. 4s2. All right. So, indicate how many unpaired electrons there are for calcium. Well, there's no unpaired electrons, right? Because in the 4s, if this is the 4s, there's just 1 orbital that holds 2 electrons, and they're both paired full. They're both in there, so it's full. So it's not. There's none that are unpaired. E. Write the condensed electron configuration for vanadium. Vanadium is argon at the core again, 4s2, but then we have 3d3. 3d3. So, indicate how many unpaired electrons there are for vanadium. Well, the 4s2 we know is full, but the 3d, there's 5d orbitals in a 3d. How do we know there's 5? Well, hopefully you can remember that 3 is the principal quantum number for this. D is the quantum number that corresponds with L, and that is what? L is 0, 1, 2. L equals 2, right? And then M sub L. M sub L equals what? M sub L can equal -2, -1, 0, 1, and 2. And these M sub L's are these right here, right? And so then that's how you know that there's 5 orbitals. And we only have how many electrons in there for going to be vanadium? Just 3. 1, 2, 3. So all 3 of those would be unpaired. Is that what the next question? Indicate how many unpaired electrons there are. So that's vanadium, or 3 for vanadium. G, iodine. For iodine, krypton is our noble gas core. Kr is our noble gas core. After Kr, we go to rubidium. That's 1, 2, 3, 4, 5. 5s, 5s2. Rubidium and strontium. We're going all the way to iodine, right? So then we go yttrium to cadmium. That's the 4d10. And then all the way to that end of it, cadmium. Then we have indium, 10, 1, 2, antimony 3, tellurium 4, and then iodine is 5. All right, so we have 5p. This is in the 5th column. 1, 2, 3, 4, 5, and we're in the p block. 5p, and there's 5 electrons, right? Iodine is the 5th. 1, 2, 3, 4, 5. All right, so. Okay, so 5s2, 4d10, 5p5. So how many unpaired electrons? Is that the next question? Indicate how many unpaired electrons. So the p orbital. What's the p orbital? 1, 2, 3, 4, 5. And we have 5 electrons. Oh, sorry. These are p orbitals, not d orbitals. So the p orbital, how did I know the p orbital only has 3? I can remember that the p orbital only has 3 because p, the L value that corresponds with p is 1, and therefore the M sub L for p orbitals is -1, 0, and +1. All right, so -1, 0, and +1, and we have 5 electrons. 1, 2, 3. I have to put 1 in each orbital before I start pairing up 4 and 5. So there's 1 electron that is not paired. All right. Okay, so we have to do yttrium, platinum, and ruthenium. Lu. Where's Lu? Lutetium. All right. So yttrium first. Where's yttrium? There it is. It's number 39. The noble gas core, krypton, 5s2, 4d1. Right? That's our noble gas core for. That's our electron configurations for yttrium. How many unpaired electrons? There's just going to be that one unpaired electron. For platinum, PT, element number 78. All right. So our noble gas core, we go back and we see that it's xenon. Xenon. After xenon, 54, we go 55 and 56. So that is xenon. 1, 2, 3, 4, 5, 6. 6s2. And then after 6s2, we start filling our, ouch. We start filling our, let's see, we have one d orbital in lanthanum, and then we start filling our cerium to lutetium. So that is 4f, right? Now these actually are in the 6th row, but because they're the f orbitals, then they are down, or the number is down two times, so it's 4f. So first of all, we have that well, let's see. They give us a little indication. Express your answer in condensed form in order of increasing orbital energy. Increasing orbital energy. In order of increasing orbital energy. Which is what we've been doing the whole time, right? Alright, so we have 6s2. That brings us from to cesium and barium. And then we need to have a 5d. 5d1 for lanthanum, that's 57. And then what we do is we go 58 to 71. 58 to 71 is 4f, and there's 14 there, 58 to 71. And after 71 comes 72, which is our 5d again, and it's 5d, 72 to 79. So it's 5d, 72, 73, 74, 75, 76, 78, 79, 8. Does that make sense? 1, 2, 3, 4, 5, 6, 7. No, 7. 5d7. Okay? So, I don't know how the computer is going to want to. Alright, so the final electron configuration could either be written this top way here, but generally you see it written this bottom way. And I'm not sure if the computer will accept both ways. I don't know exactly what they're looking for, but they're essentially equivalent. Alright, so then the question is, how many unpaired electrons are there, right? How many unpaired electrons are there in platinum? Alright, so platinum here, the 6s2 is filled up, the 4f14 is filled up, so none of those are unpaired. But the 5d8 is not filled up. In fact, what does it look like? Well, there's 5, 2, 3, 4, 5. How did I know there's 5? Because that D is equivalent to saying L equals 2, and L equals 2 means M sub L can equal -2, -1, 0, +1, and +2. -2, -1, 0, +1, and +2. And each one of these orbitals can hold 2 electrons. So that's 1, 2, 3, 4, 5. We have to fill them all with 1 before we start pairing 6, 7, 8. So there's 2 unpaired electrons. All right. The last example here, Lu. So Lu is right before platinum by a little bit. So we have to take off how many electrons? 1, 2, 3, 4, 5, 6, 7. Down to half mu. And then Lu, lutetium, has the 4F14. So the only difference is this. So the xenon is the core still, 6s2, 5d1, that's the lanthanum, and then 5d14, or 4f14. So how many unpaired electrons are there here? That one there should have only one unpaired electron, which is that 5d1, which is unpaired. All right, so that is number 10, 10th problem that we had. Number 11, problem 671. Express your answer. Identify the specific element that corresponds to each of the following electron configurations. So now we're given the electron configuration: 1s2, 2s2. That's beryllium, right? Because 2s2, 2, second row, s block, 2 electrons in. So that's beryllium. First one, assuming that they're all ground state electrons configurations. All you really have to do is go to the last little bit there, which is for part B, 2p4. You go to the second column, second row, p block, 1, 2, 3, 4. So that's got to be oxygen, all right, argon, 4s1, 3d5, okay? So identify the specific element that corresponds to each of the following electron configurations. So the problem here, argon, 4s1, 3d5, that is an excited state, 1, 2, 3, 4, 5. So if you stop at 3d5, you're on manganese, but 4s isn't quite filled. So one of those has to come down and fill the calcium. So that's actually going to be not manganese, but chromium, which is Cr. So this is an example here that they didn't tell us that they were going to be using excited state electrons, but they are. They did then. All right? I guess it didn't say necessarily each of the following electron configurations. So it doesn't say that it has to be ground state, so it might be an excited state. Now in an excited state, the only thing that's different is that some of the electrons, the subshells below, are missing electrons because they've been moved up to a higher shell. So let's use that chromium for an example here in just for a second. And let's say here's our nucleus for the chromium, right? The electron configuration for chromium is argon, and then we have 4s2, 3d4. 4s2, 3d4. That's the electron configuration for chromium. Now what they've shown us is 4s1, 3d5. So this is chromium. But they've shown us argon core, 4s1, 3d5. So what's happened is that second electron, so let me draw the 4s orbital, so I'm going to label this 4s. It's supposed to have 2 electrons in it. And then we have the 3d orbitals. Now those I'll draw like this sort of thing, right? 3d orbitals. And you know, this gets kind of messy. So maybe I should just draw it like this, where here's the nucleus, right? And I'll draw the 4s orbitals as just a ring, and then the 5, or the 3d orbitals, which are higher in energy, as a ring as well. The 4s contains 1 electron, the 5d contains 1, 2, 3, 4, 5 for this excited state. Now, how is this an excited state? Well, what's happened is the electron that was here moved up and is now here in this higher state. Does that make sense? I can tell because I see that one of the electrons is missing in one of the subshells or shells which is lower than it's the location of the electrons. So essentially, what I do is I pretend like this has come back down, and so then I fill this up with 4, make this 4s2, and leaves me with 3d4, and then that is what I'm going to use to identify what the element is. All right, so that's chromium. Part D. We have krypton. After krypton is our 5s, right? So krypton is in the 4th row, 1, 2, 3, 4. So 5s2, those are all full, and then 4d10, that's all full, and then 5p4. So 1, 2, 3, 4. So that's tellurium, Te. All right, because 5, 5th row, p block, and then 4 electrons, and that's how we get that element. Is that the last one? That's the last one. All right, so that's your homework for Chapter 6, the 4th day.